Welcome to this webinar from Magnetek regarding improving efficiency and process controls with variable frequency drives. This relates to use of drives in underground mining applications. My name is Ed Booty. I'm the Director of Elevator and Mining with Magnetek. I've been with Magnetek 32 years. I have a Bachelor of Science degree in Electrical Engineering from the University of Illinois, Urbana-Champaign. In my time with Magnetek, I've had the opportunity to work with a number of motor and drive-related industries and applications. Our topics today will primarily hit on these three major points. Felt it's very important to go back and start with a review of motor and drive technologies. Then we'll talk some about optimizing the electrical system efficiencies in specific applications using variable speed drives, notably fans, mobile mining equipment, and a rather unique power system seen in underground mining, 1,000 volts. Lastly, we'll touch on improved diagnostics with equipment based on using variable frequency drives or variable speed drives, and the benefits that the microprocessors of those drives today bring to the operators. First, let's start with a brief discussion of the most common types of motors you'll encounter in underground mining applications. First would be three-phase AC induction, or squirrel cage motors as they're commonly called. This is the most common motor seen in industry. It is readily available as an explosion-proof device. It is generally seen across the line and operating at a fixed speed based on the incoming power of the system, whether it's 60 hertz or 50 hertz. And it does, though, lend itself well to be operated on variable speed drives. If you look at the chart in the upper right-hand corner, there are four types of speed torque curves that one would encounter with induction three-phase squirrel cage motors. These are defined by National Electrical Manufacturers Association, or NEMA. The next common type of motor one would see in mines would be DC motors, and there's basically shunt or series style DC motors. They have unique benefits and characteristics to each. It should be noted that DC motors do require a type of speed control to be used. Generally, DC is not available in overhead power lines to run the motor. They are available explosion-proof as an option, though it's a little bit more difficult and more costly with DC motors. If you look at the charts on the right-hand side, middle and bottom, it looks at a typical speed torque curve of a shunt motor and a series motor. As you can see in the bottom chart, a very high amount of torque at low speed, and so generally series motors would be used in traction applications. Another type of motor one might see is switch reluctance. This is a rather unique style of motor. It does require an adjustable speed drive as well. It is also seen in mostly traction, but some just unique applications. Permanent magnet motors are becoming more common in a variety of industries, although in mining it's still not allowed by Mine Safety and Hazards Administration, though it is pre-magnetized, so it does require adjustable speed drives as well. It cannot be operated across the line. If we take a look at common types of drives themselves, the most common one we'll see is going to be adjustable frequency drives, pulse width modulated, or PWM, variable speed. It is seen throughout industry today in both low and medium voltage capabilities, and by low voltage we typically talk 480 volts, and medium 2300 or 4160. A little bit more on that further in the review today. It's the only AC technology, though, that does operate or can be operated directly from a DC source, such as batteries, and that does lend itself well to certain mining applications, which we'll touch on. It can be made regenerative, meaning as you stop the moving machine that you're connected to, be it a conveyor or something like that, that any energy that's being driven back to the line or to the drive can actually be put onto the line and reused. Six-step variable frequency drives, it's an older technology. This is a variable voltage. If you think about PWM and variable voltage, it's kind of like an FM signal and an AM signal. The PWM is a fixed amplitude, whereas the sixth step is a varying amplitude. Again, it's an older technology, not seen so much today. Current source inverters, they've been around a long time, one of the earliest variable speed technologies. Generally today you see this in higher horsepower applications. By its design, it is regenerative, one of the benefits of that product. And lastly is silicone rectifier or SCR type of drives. This is generally what one would see for a DC drive. It's also available in regenerative and non-regenerative designs. Mechanical variable speed. Again, not every time is it electrically controlled, but oftentimes mechanically controlled in mining. Eddy current clutches would be one of those types of designs. In this case, you have a motor operating at a fixed speed and an output shaft that's controlled by electrical controls on a clutch coil, and you can adjust the speed output from that. It is a very good application when it comes to shock loads, oftentimes punch presses, those types of applications, or high shock type of applications. Hydraulic variable speed couplings, typically they're on higher horsepower applications as well, and the power is directly transferred through the hydraulic fluid from a constant speed prime mover to the load that you're operating. An older technology that one would still see is variable pitch shivs. If you think about this, you have two shivs with a belt in between, and as one size gets larger, the other gets smaller, changing the gear ratios, if you will, for varying speed. One of the problems is relatively high maintenance, running grooves in the shivs and mechanical wear and tear. Another thing to consider is that all of the mechanical variable speed we've discussed above have a constant speed prime mover, typically a motor, or it could be an engine, and they generally are much less efficient than electronic controls as the speed is reduced. If you draw your attention to the chart on the right-hand side, you can see that a variable frequency drive operates from 85 to high 90% efficiencies across a range of 50% speed to 100% speed, and comparing that to varieties of other mechanical types of speed controls and the lower efficiencies that you see with those as speed drops. Now, we talked a little bit about speed and torque, but let's look at a practical use and types of applications that you would see in mines. First is a variable torque type of a device. Most commonly, this would be centrifugal blowers or centrifugal pumps, and as you can see in the lower left hand, they follow the affinity curve of horsepower required is a cube of the speed, torque required is a square of the speed, and this does lend itself for significant energy savings as you vary the speed down, and we'll do a specific application of that. Most commonly you see in applications would be constant torque, compressors, conveyors, positive displacement pumps, gear pumps. And the characteristic here is that your torque output remains constant from essentially the starting of 0 speed through 100% speed, and therefore your horsepower varies directly with the speed. If we do a quick comparison of the types of variable speed drives and are they good for constant torque or variable torque, turn down ratio, meaning from 100% speed, how low can I operate, how much of a reduction can I see, and the efficiency that one sees across those ranges, and finally comparing to installation and maintenance costs, it's readily apparent that for both constant and variable torque speed applications, variable frequency drives lend themselves really to be the optimum choice. You have a high turn down ratio of 30 to 1 or as high as 1500 to 1 if you use an encoder feedback, which is essentially from 0 to 100% speed, and a very high efficiency throughout those ranges, relatively low installation costs and low maintenance costs with those. Now let's take a look at some specific applications as one applies a variable frequency drive and a three-phase motor. The first will be, we'll look at centrifugal fans. Now in this case, we've picked an outlet damper control versus variable speed. So we're going to be comparing a fan running at a constant speed and then throttling the output of the flow to varying amounts as compared to driving the fan at lower speeds to get the amount of airflow that you want. In this case, it's a 600 horsepower or 450 kilowatt machine. And for purposes of this evaluation, we're looking at a continuous operation where the utility costs average 8 cents a kilowatt hour. Now, as we talked about, your application, fans are designed to run at 100% speed at a very small amount of time, the worst case conditions, if you will, boundary conditions. So in a typical fan application, you may only see 2% of the time running at 100% speed. In this case, we also then selected 5% of the time running at 90% speed, 20% of the time at 80% speed, 38% of the time at 70%, 25 at 60, and 10 at 50. And this is either speed or the flow, so we can compare these directly. Again, if you look between a damper control and adjustable frequency drive, at 100% power, they're both seeing 450 kilowatts. But as you reduce the speed or the amount of flow that is required, the difference in power requirements drops rather dramatically. At 80%, when you outlet damper, you need 310 kilowatts compared to only 267 if you're varying the speed of the fan itself. But if you go all the way down to 50% speed, you had 139 kilowatts in a damper control compared to 82 when operated in variable speed mode. And again, following the affinity laws in the lower left-hand corner, you can kind of see how horsepower requirements go down with the cube of the speed. In this case, to run that fan and outlet with an outlet damper at that duty cycle, it would cost $171,524 per year. Compare that to operating on a variable frequency drive, which would only be $137,000. So that's a $34,524 savings annually. That goes a long ways towards the addition of a drive into this application. Next, we'll look at what we call an untethered mobile machine. By untethered, we mean a machine that's going to be self-propelled either by electric or diesel power. Oftentimes, machines are tethered to a main power cable, and they have to run on a fixed route within the mine. So by going untethered, it allows greater accessibility and increased safety. Typical machines would be scoops, LHDs, bolters, drills. One of the goals here is to reduce or eliminate the diesel power from the vehicles. And there's reasons why mines, especially underground mines, are looking to reduce the amount of diesel power. One is improved air quality for the laborers. You have to have a certain air quality within the mine, and that requires a tremendous amount of air changes within the mine for the operators. As we saw in the example prior, if you can reduce the amount of ventilation flow in the mine and still have a very safe working environment for the laborers, there can be a significant amount of energy savings in the fan as well. But within the machine itself, by reducing from diesel power to electric power, there is a savings also to be seen in refueling costs, etc. Typically, if you replace the diesel with electric, there's two types, 100% battery or a hybrid, where you may have a smaller diesel generator and an electric assist. In the case we will be discussing here, we're looking specifically at battery-powered machines. And in this case, we actually went from a lower voltage battery pack to a higher voltage battery pack, namely 128 volts to 240 volt battery power. MSHA does allow going up as high as 300 volts with the battery pack for a maximum. In this case, we replaced old DC controls with new AC controls. So the DC motors were replaced with AC, and the drives themselves were replaced from SCR type DC to PWM AC controls. What did we see with this conversion? Well, first, much improved overall performance. Speed regulation, load capacity was directly impacted. With an AC drive, we were able to hold a constant speed regardless of the grade and pitch, whether we were going down a hill, up a hill, we were able to maintain a constant speed. And again, if we were going down a hill, the battery is able to be recharged from the regeneration from the AC motor back. Our speed and torque profiles could be adjusted easily by the operator. So in our commissioning and setup, the operator was able to make the machine feel or work in an optimum way that for their particular driving habits. Another benefit is with AC drives, we can easily set a maximum speed. Again, many mines do have a requirement for safety that vehicles do not exceed a certain speed, and that's relatively easy to set up with an AC variable frequency control. Again, as we mentioned, the regenerative benefits of energy captured putting back to the batteries helped to lengthen the amount of time in operation between charges. Additionally, by going up in voltage, we saw a reduction in temperature. Power is approximately equivalent to voltage times current. So if our voltage goes up and our power is constant, then our current will go down. And current is the primary loss of most electrical systems. In fact, it's the square of the current times resistance is your losses. So I squared R losses are significantly dropped. In this case, if you drop your voltage or your current in half, your losses can be cut in a quarter. Additionally, we improved our setup and diagnostics by changing this technology. Again, easy parameter setups and diagnostics directly from the cab of the machine. So let's look a little bit at some of the savings that we recognized with this. Again, first is the elimination of significant amount of maintenance costs related to the DC motors. Again, DC motors have commutators and brushes. They are in explosion-proof type of enclosures, which makes it more difficult to access them. So this is a relatively big maintenance item that were totally eliminated. AC induction motors have no brushes or commutators associated to them. Further, because of the reduction in the amount of currents, we greatly reduced the operating temperatures within the control box where the drives are actually located. And temperature is a big issue in any electrical product. The more you can reduce the temperature, the more you lengthen the life. In this case also, the mine saw a great reduction in cable connections, in failures of those connection points. Over time, as current is passed through those connectors, you'll get stressing and fatigue, particularly in joints. And again, the more current you can reduce, the longer the life of those cables. What this mine in particular saw was that a DC machine had a general availability of about 85%, and their AC machines, once installed, were over 99%. Part of that benefit was the fact that with an AC machine at 240-volt DC battery power, we were able to go between 8 and 10 hours, so a full operating shift on a single charge. The DC systems typically had about a 6-hour operating point, so you would have to swap out a battery pack on one of these machines mid-shift, and that would, you would lose about 30 minutes in doing that on a per-shift basis. So that also affected both availability and overall productivity of the mine. Now, new battery technologies are coming out, lithium-ion, things like that. Not all of those are approved yet for use underground with MSHA, but the benefits they do offer will be a much shorter recharge time and longer life of the batteries themselves. The third point we wanted to talk about in terms of underground mining applications would be a rather unique area of 1,000 volts, or in this case, as we show it in the lower left-hand corner, 995 volts. Typically, coming into a mine, you'll have utility scale voltage. In this case, we have 115 kV utility to supply. That's going to be dropped down to a distribution voltage. In the illustration here, we're using 13.8 kilovolts, 34.5, also a very common distribution voltage out there. And from there, it's further dropped generally to 4160 or 2300 volt for operating directly machines, ball mills, conveyors, could be fans, things like that. Further from that point, typically you'll drop down to 480 volt three-phase. This would be the most common voltage around internally for operating a variety of different kinds of conveyors, other machines, pumps, fans, the like. Lastly, 120 volt single phase would be tapped off of that for operating your command and control, lighting, computers, those types of equipment. A unique branch, though, in underground mining is this 1000 volt, or just under 1000 volts. MSHA has viewed medium voltage really at beginning at 1000 volts and above, whereas the National Electric Code, NEC, generally looks at anything above 600 volts being a what they would call above low voltage. But MSHA does allow up to 1000, and that has become the most common voltage for a variety of applications: continuous miners, shearers, shuttle cars, conveyors, etc. One of the benefits of a drive, a variable speed drive at the 1000 volt, is it really gives you the opportunity to kind of blend the best of two worlds. Again, as we talked earlier, power is approximately equal to voltage times current. So if you're able to go to a 1000 volt system, it's going to run about 50% of the current of a 480 volt system. And therefore, with reduced currents, we talked about the benefits of heat and other things. There are two basic types of outputs that you would see from a PWM variable speed drive, and those are noted on the right-hand side. A two-level, that's the top chart, shows the pulsing of your output transistors in both a positive and a negative phase, the blue pulses that you would see. And the red sine wave is essentially the current that the motor will be experiencing in operation. So a two-level control is most common in 480 volt drives. It's an option with 1000 volt, and we'll talk a little more on that, but it's very rarely seen from medium voltage style, primarily because of availability of transistors at the high voltage levels. Output transistors need to be sized at about 2.5 times the input line voltage. So finding voltage, IGBTs of that voltage rating are very scarce. Three-level control, though, is pretty much the standard that one would see on a medium voltage drive. It's very rarely seen on 480, but it really is an ideal option for 1000 volt. And if you look at the lower chart on the right-hand side, you get an idea of what a tri-level or a three-level control looks like. Now, instead of a single pulse in the positive and in the negative direction, you have two pulses in the positive and two pulses in the negative. It allows for a smaller voltage per device, and you still get, it's a little hard to see there, but there's the same sine wave of current passing through those pulses. So your motor still sees a very clean current waveform. If you compare tri-level, two-level, 480 and 2300 by some key drivers, let's look at cost, cable lengths, things like this. Generally, the lowest cost drives out there are going to be, two-level 480 volt. But in a 1000 volt system, it does require higher voltage devices, which are more expensive. So actually going to a tri-level where you're using twice as many devices, but at a commercially available 1200 volts PIV, which is in the middle of the chart, compared to 2500 volt, which would be a typical standard rating for a device you'd have to use for a 1000 volt drive. There's a big difference in cost between those two. So even though you run more devices, it's a lower overall cost. It does allow for much lower audible noise. Maybe not as big of a deal in some mining applications, but anytime you can reduce audible noise, it is better for the operators that are in close proximity. Switching frequency does allow for a cleaner sine wave to the motor that allows for less losses within the motor itself. I briefly passed over, but the drive to motor lead length in a two-level control, generally greater than 75 feet between the drive itself and the location of the motor, it's recommended to use a filter for reducing harmonics on the line out to the motor. In a tri-level or a three-level control, that can be extended to around 1,500 feet. So many applications within the mine would not require any type of filtering between the motor and the drive itself on those long leads. We looked at the different voltages one would use for the power devices, and if you look at this from an efficiency standpoint, these higher voltage devices are much less efficient. They switch at a lower speed, and so there's higher losses every time they're switched. So you end up with even a lower efficiency than you would like. So if we compare the trade-offs of 1,000-volt applications, yes, it's going to have more IGBTs regardless in comparison. But comparing a 3-level to a 480-volt, and in this case we're using a 1,000-volt with a transformer stepping down to 480 and a transformer stepping back up from the output of the drive to 1,000-volt. You reduce that the amount of heat and losses and costs that you would have with the two transformers. In comparison to a 3-level to a 2-level on a higher voltage drive, you definitely get the benefits of the smaller voltage on each drive IGBT with the tri-level compared to 2-level with a much higher voltage device and the losses associated. Lastly, we'll look a little bit at some of the diagnostics and benefits of a drive. Generally, the newer inverters today have microprocessors that a lot of brain power within the drive itself. In the ideal situation, you want to be able to connect the drive up to other devices and be able to share information. Generally speaking, drives today have built-in connectivity to a variety of networks: CAN, Ethernet, typical RS-485, or even custom protocols allow for accessing of information within the drive, better diagnostics of the operating parameters of the machine. This is directly allows operators to get access to faults, diagnostics, other status, and also allows them to log in and report capabilities or issues that might be happening within the inverter and in the operation of the machine. Additionally, safety can be improved significantly. The ability of interconnecting proximity detection systems, other things on the network with the drive provides for greater safety opportunities, and integration of wireless controls, the ability for an operator to be at a safe distance from an unsupported area of a mine and still operate a machine by being off of the machine and outboard. So in summary, we talked about varieties of types of motors typically seen in underground mines, AC and DC in particular. We also reviewed electrical and mechanical speed control methods, efficiencies that one would see with those, and we came to the conclusion that AC PWM drives is really the most common and most efficient of the varieties of opportunities we have there. We looked at a variety of applications, in particular an HVAC fan application, comparing outlet damping to varying the speed. We looked at traction of a converting from a DC control to AC control on a battery-powered machine, and 1,000-volt drives that are becoming more common in underground mining applications. Lastly, we touched on benefits of integrating drives into control systems for better diagnostics, better feedback, and better safety for the operators. Magnetek does provide a number of links to different articles, etc., that would be used in this presentation, and this is available here as well as available from the www.magnetekmining.com, where this webinar was made available to you. Thank you.